Okay, we're going to continue with talking about neural networks. Now, this is the funny part. It's kind of rough to talk about neural networks anymore because neural networks have become so ubiquitous. Talking to Justin Bowie, who you saw the PhD final examination of, I wonder about the knowledge of the details of the inner workings of neural networks. So we're going to just touch on that, and I hope that Dr. Pablo Rivas or Dr. Dong touch on it also, as opposed to just being keyboard engineers. I think a lot of people just know about the existence of this high-level software, go out, they jump in without really any understanding of what happens. They know what happens when you put an input in and what happens when you generate an output. But there are many that do know the workings of neural networks. I certainly don't want to be dismissive of everybody. So let me go ahead and continue the lecture where we left off before. And I'm going to share my screen. I think I'm going to share my screen. Yes, I am going to share my screen. I clicked the wrong button. And we're going to talk about first of all, the McCulloch-Pitts neuron. And I get McCulloch-Pitts and Hibb, the dates mixed up, but McCulloch-Pitts gave this analytic model of a neuron long time ago, at least let's see, 70 years ago. Okay, but here's the idea of the neuron, and this is the neuron that is even used today. This is a single structure in the area of artificial neural networks. You have states, and I'm going to draw in here these states, S1 through S2. Now, what are these states? These states are either the states of other neurons that appear to the left of this neuron, and every neuron has a number assigned to it as the state of the neuron, the small s. And so this s can come from another neuron, or it can come from a stimulus, the input layer, if you will. And then the entire idea is that each one of the inputs is weighted by weights, W1, W2, et cetera. And then the sum is added up, as you can see in this formula. And then we don't want things to get kind of crazy. So we submit it to something called a squashing function. And a squashing function takes the F and it compresses it. It compresses it to a state either between -1 and 1 or 0 and 1 or some such thing. So it's referred to as a squashing function. In fact, some of the functions that are used today don't even squash anymore. They suppress negative values of the sum and they let through everything that is a positive sum. So here is an example of a squashing function. Now, if you remember, the squashing function takes the sum here, and it squashes it into a smaller interval. So the most commonly classical used squashing function is referred to as a sigmoid. As you can see here, boy, white doesn't show up on white. So the input can be from -infinity to infinity, and this is the equation. You can see it, just make it out in the left-hand figure, 1/1 plus e to the minus x, and that is a sigmoid. It's an interesting curve. One of the interesting things about it, let's see if I can change colors here. I can change colors, okay. Yeah, yay for me. One of the interesting things is that there are many alarmists who come out with exponential growth. And the beginning of the sigmoid looks like exponential growth, doesn't it? And we see this when I was a kid, it was population that, my goodness, if life continued and we kept populating the planet the way we did, that pretty soon we would have one person per square inch around the world and we'd be really rough off. Well, another place is Ray Kurzweil. Ray Kurzweil's book, The Singularity, he talks about the exponential increasing of say, the speed and the capability of computers, for example, is measured by Moore's law and other exponential things. And he said, this is incredible because AI is soon going to take over because of this exponential curve. Well, it turns out that no exponential curve is maintainable. You will never have an exponential. It always levels off. I mean, one of the places that we saw this most recently was with COVID, right? That the COVID epidemics came up and everybody talked about leveling off the curve. Well, they were trying to hit this sigmoid. It's called a sigmoid because it's S-shaped. The reason that we're interested in this particular formula is because it's easy to differentiate. We have over here on the left the expression, on the right, the expression for the sigmoid. And here's what's cool. If we take the derivative of it, we get the original function times 1 minus the original function. This turns out to be very important in training the neural network because it says that we don't have to actually do derivatives. Instead, we can just take the value, whatever it is, if we want the derivative of f, and we just take f and multiply it by 1 minus f. You'll notice that the sigmoid compresses things from minus infinity to infinity into 1. By the way, this is a concern about neural networks. You notice that on the previous slide that we were taking values of the sum and we were compressing it using the sigmoid function. Can you see that if the input, the sum is, 5,000 or 500 or 100, that the output, the state of the neuron is going to be 1, right? There's a saturation. And this is something which if one uses the sigmoid, you can be concerned about that your neurons get saturated. And once they get saturated, you can't wiggle things anymore. You have no freedom of wiggling what's going on. And so there's techniques to do that. There's techniques to do that. There's techniques to mitigate this so-called neuron extrapolation. Something very similar to the sigmoid squashing function is the see, I had my prose just right, and I'm not getting a transition here. Why aren't I getting a transition? None of my keyboards are working. Okay, I can't even hit escape. I mean, escape should make it little, right? Okay, so I'm gonna stop sharing and then I'll try to share again. There's Innocent, we were talking about you. Glad you can make it. Okay, something very similar is a so-called hyperbolic tangent. A hyperbolic tangent is basically a scaled sigmoid. If we take this sigmoid, oh, guess what? Since I restarted it, it reset the color. Okay, there we go. If you take the sigmoid and kind of stretch it, okay, kind of stretch it down, it's exactly mathematically the same as the sigmoid. So it's the sigmoid kind of stretched to go now between -1 and 1 instead of 0 and 1. It also has this very nice relationship with the derivative that if we differentiate this hyperbolic tangent, we get 1 minus the hyperbolic tangent squared, or 1 minus f squared. So if we have to differentiate this function, we don't have to go and do weird stuff. We can just take the value, whatever f of x is, and we do 1 minus f squared, and that gives you the derivative of the function. So that's a nice property that turns out to be very nice in neural network sort of architecture. Okay, you know what? For some reason, the screen sharing is being trumped by my keyboard. Therefore, I'm going to have to use the regular mode instead of the presentation mode, which I don't like. So here is the concept of a layered perceptron. This was in vogue in, I don't know, the late 1980s, 1990s. People took the neural networks and they did incredible things. As engineers, we're interested in the theory of neural networks. We're interested in papers, of course, because they're fun, but I think ultimately we would like to see neural networks being reduced to practice and used. I believe that I mentioned in the beginning that two of the big areas that came out of neural networks were application to power load forecasting and forecasting in general, and also financial markets, things such as credit fraud. So here is the basic layered perceptron. We have a well, guess what? Now my marker isn't working. Okay, this hurts my feelings. Okay, I'm just going to have to point with my pointer and you're going to have to follow. This is very suboptimal and I don't like it. And now my pointer disappeared. Okay, life is rough. My daughter calls these first world problems, right? Okay, let me try to make it big again. I don't know if it's going to freeze or not. Okay, now it's working really good. So anyway, what you have is you have an input. You have an input down here. You have so-called hidden layer, and you can have a number of hidden layers. And this is the general vanilla artificial neural networks. And you have a corresponding output. Each of these little dots here are referred to as neurons. And you can see the model of our previous neuron here. We have a bunch of inputs. And these inputs are generated by interconnects, and each one of these interconnects has a weight. And what's going to happen is that each neuron performs a simple calculation and is assigned a number, a state associated with it. And then that state is used to propagate up to the next neuron. There is, believe it or not, still no consensus on what is called a neuron. Some people do not like to call interconnects on the input nodes. They don't like to call them neurons. They're not doing any computation. They're just spreading out their information. But yeah, clearly this is a neuron, and the output can also it does a computation. So yeah, it's a neuron. So this is the basic idea. And again, we can have numerous different results. Numerous different results. And by the way, the output is determined by the weights. And the whole idea behind the neural network is to wiggle these weights, these interconnects, so that given the proper input, we get the proper output. So here is what we're provided. We're provided with labeled data. As we said, we have an input vector set, which is here, and we have a corresponding output target vector. So each one of the inputs is given a label. So this might be a picture of a sumo wrestler, and P sub 1, I sub 1 is a sumo wrestler, and P sub 1 said that's a sumo wrestler. And I sub 2 might be a basketball player, and P sub 2 would be that's a basketball player. So we have each one of these labeled. Now, your P sub n is what you want. We would like the neural networks, given these inputs, to give out what we want. And the question is, at least in the rudimentary sense, is to find the weights of the interconnects using training data to minimize the error of the test data. So we have the inputs, we have the target value, this is what you want. But the neural network is not going to give you what you want, it's what you get, okay? And would like to make the output, what you get, equal to what you want. And the difference, the error between the two is what you want down here minus what you get. And you square that, and that is the corresponding error of that set of weights. So you'd like to adjust the weights to make this error a little bit smaller. And that's a vanilla explanation of how to train a neural network. So the error is a function of two things. This is kind of weird to think about, but it's the fixed training data. The test data, the fixed training data, the so-called test data are fixed. So everything has to revolve around this training data. And the thing that is not the thing that we have to wiggle and we have to determine is these neural network weights. There are a whole bunch of different ways of doing this, and most of these work very well for medium to small size neural networks. But if you go to the large neural networks, like convolutional neural networks or deep learning, you need to use aerobatic propagation for reasons that I will mention as when we get to it. Okay, everything seems to be working down here. Okay, the idea of minimizing error, it's steepest descent. If you think about it, remember we talked about fitness landscapes, right? These landscapes that if you had different inputs, you would have a different fitness associated with them. We talked about a pancake, and these pancakes had, a certain test. Well, here we have a landscape, and that landscape is the error. And the space it exists in is this space of weights. We have the first weight, the second weight, very high dimensional space. It's ever how many weights there are. So we have this, we have to visualize this landscape in this very high dimension. And what we'd like to do is we would like to step downhill. Now, there's a couple of ways we could step downhill. One way is we could look at all the weights and then maybe change a couple of them and see if we got better. That would be stochastic hill, not hill climbing, but hill sliding, I guess. What's the opposite of climbing? It's going downhill. But there's a better way to do it, as discovered by people such as Bernie Woodrow at Stanford and Frank Rosenblatt. One is to look at the error and recognize that we have an error and that this error has a derivative associated with it, right? But what we would like to do is we would like to find out the derivative of this error and take the negative of it. Because the negative of the derivative tells us how to get downhill. That points in the proper direction. Then we have to do something. We have to choose a step size. Once we determine downhill, we would like to choose the step size. And that step size is referred to as eta. And so the new value of x is equal to the old value of x minus the step size, if you want to take a little step or a big step, times the direction of downhill as measured by the error function. By the way, this is very idealized. For example, suppose that your error function looked like this and had numerous minima. You get into problems there, don't you? And I've asked Adam Goad, who has done some work in simulated annealing, to show how we can work ourselves outside of these local minima. It's not 100% guaranteed. By the way, nothing in search is ever guaranteed. You're never guaranteed that a search is going to work. And that, that's unfortunate. You're never guaranteed that what you get is the best. But as engineers, we look at a certain criterion and we have to match that criterion. And when we do, all is well. So I'm going to give you a simple example of a one-dimensional function. This is an error function, which is 1/2 x squared. So this is a parabola. And the minimum is that x is equal to 0. And we want to start out, this is x, and this is the error as a function of x. We would like to find out which way is downhill, and let's assume that we don't know that the error is 0, because in general, we're not going to know the function of error. We're just going to be able to access it one point at a time. Here we know the entire idea. So the negative derivative is minus x. So minus x points downhill. And so we're going to replace x by going downhill times the step size. And guess what happens if your step size is too big? Can you kind of see intuitively what happens? If the step size is too big, you're going to overshoot. If you take the step size too small, you're going to have something which is critically damped. It's going to take you ever, not critically damped, but over damped. It's going to take you ever to get there. So all of these optimization algorithms always have parameters that you need to choose. Oftentimes these parameters are suggested, but one size doesn't fit all, but it might in your case. So therefore, again, we take the new value of X, we subtract off going downhill times the step size, and that turns out to be 1 minus eta times X. So if P indexes the iteration, the Pth iteration is equal to 1 minus eta times the P minus 1 iteration. And you've all had Z transforms and iterative things. This is a geometric series. So if we look at some initialization, we find out that X of P is equal to 1 minus eta. And if we do this P times, this is simply raised to the Pth power. So that gets us downhill. And we notice that as P goes to 0, P goes to infinity. If we have a number which is less than 1, if 1 minus eta is less than 1, I guess I'm writing what I have here on the bottom. If 1 minus eta is less than 1, this thing goes to 0, doesn't it? So it gives us our proper result as long as your step size is appropriate. So your step size has to be appropriate. It can't be overdone or underdone. So let's see if we can apply this then to the neural network. Let's take this is called a perceptron or an Adeline. They're kind of the same. There's specific differences. The perceptron was invented by Frank Rosenblatt, I believe of Cornell, and Bertie Woodrow did the Adeline. And I believe it was the Adeline that used this. And Bertie Woodrow didn't have any hidden layers in his neural network. So we have the error now. The error is equal to the summation of the output minus the input. Don't forget, this is what you want, this is what you get. So we'd like to make what you get what you want. What you want is fixed. That's the label on your training data. Now, this output is simply equal to the summation. Remember our model of the perceptron. It's simply equal to the summation of all of the weights connecting to that neuron minus P sub n. This is still what you want. So we're computing this result. So the cool part about this is we can literally take the derivative with respect to the weights. Remember, our error exists in this very high, well, in this case, it isn't that high dimensional, but in general, a very high dimensional space. And we need to figure out which way is downhill. So the error with respect to the mjth weight is equal to this result. If we want to do this. Now, here's the cool part. Here's the cool part. This is just O sub m. So therefore, the rate of change of error is equal to the input divided by what you want minus what you get. I think I have this in the next slide. If I don't, I'm going to come back and elaborate. Yeah, this is really cool. So therefore, if we want to update this weight, and this is the beauty of aerobatic propagation, please appreciate the beauty of it. The only thing we have to know is we only have to know this input and we have to know this output in order to update this weight. So if we have an interconnect, a weight, we only have to worry about what is happening at both ends of the weight in order to update it in accordance to this steepest descent algorithm. And that is beautiful, because what it says is that the update of the weight here has nothing to do with what's happening with the neural network over here. I don't know where that went. Okay, that the update of the weight here has nothing to do with what happens to the neural network over here, over here, over here. It's totally a local phenomena. The biologists love this because they said that, that makes sense in the brain. If you interconnect two neurons on this side of the brain, it shouldn't depend on what happens on this side of the brain. It should just be the two neurons. So the update is totally local. And that, again, is the beauty of aerobatic propagation. And other techniques don't have this beauty, that the update of weights is dictated by what is happening elsewhere in the neural network. But with the steepest descent, it's totally a local phenomenon. So therefore, W21, as you can see here, is just equal to the old value of the weight minus the step size, which is something you have to choose, times I4, which is what connects us at this end, minus O2 minus P1. So up here we have O2, and that's what we get. And we have, I'm sorry, O2 minus P2. P2 is what we want. So the difference between those is the value that we use here. Totally a local optimization update. So this is really kind of cool, except that there's a problem. And one of the problems is that what happens if we look at all of the input that gives us an output of 0? Is that okay? So we're going to look at all of the possible inputs that give us an output of 0. And we're going to say, if the output is greater than a half, announce class 1, basketball players. And if O is less than a half, announce class 2, which is sumo wrestlers. Now, there's more sophisticated ways to do that. We'll talk about softbacks later on, but let's just use this for right now. So what happens is that the boundary, remember we talked about the boundary between the sumo wrestlers and basketball players, has to go through the origin. It has to go through the origin. This in higher dimensions is the equation of a plane, and that plane goes through the origin because if you look at all of the inputs, this is the equation of a hyperplane in higher dimensions. And this is not good. This really limits what we do, because what happens here is that this classification boundary always must be aligned. Remember, we talked about the domain expertise that you have to figure out when you're doing stuff like this. So that's no good. So how do we get away from that? Well, we get away from that by adding another neuron to this. And this neuron over here is called the bias neuron. And you'll see the bias neuron used in neural networks all over the place. What the bias neuron does is it takes this line, and instead of this inner product being equal to 0, it's equal to the bias. So therefore, it doesn't have to go through the origin anymore. So we treat this with, it doesn't matter what the input is, this is always 1. This is always 1. This is always 1. And then we update these interconnects again and again and again as more data that begins to come through. So the classification boundary is still aligned, but it need not go through the origin anymore. And that's a much better generalization. So you will see, even in the most rudimentary neural networks, you will see this bias neuron. Now, Minsky and Papert came out with a book called Perceptrons. There was a big fight between so-called connectionists and rule-based systems, if you will, or in the late 70s and, well, the 70s in general. And it's one of these things which historically was fueled by pride, and the idea is what I have is best. There was Minsky and Papert at MIT. Minsky had fooled around with neural networks, but he liked this rule-based system. You know, like the fuzzy system. The fuzzy system is a rule-based system where you have a bunch of rules, but you try to extract those rules from an expert and reduce it to code. And they didn't like this work of these mavericks, Bernie Woodrow and Frank Rosenblatt. And they said, you know, this neural network is no good. And they wrote a book called Perceptrons, and it trashed neural networks, and it trashed it badly. And one of the things that they said, this is the classic example that they used, is remember that perceptron that had no hidden layers can only do a line. And they came out and Minsky and Papert in the book Perceptrons say, you know, think of this, XOR, the exclusive OR. Here's the exclusive OR, right? 0 down here, a 0 up here, a 1 up here, and a 1 up here. You're all familiar with the exclusive OR logic operation, right? So Minsky and Papert came along and said, you know what? This is a very, very simple classification problem. But you can't use a line to separate these X's from these circles. You can't do it with a line. And if you can't do it, their point wasn't the exclusive OR. Their point was, if you can't do it for something as simple as the exclusive OR, certainly there is going to be more complex operations that are not treatable using this technique of the neural network with no hidden layers. So as a result of that, neural networks kind of faded. It went into a so-called AI winter. And there was not a lot of funding was cut. There was also something in Britain called the Lighthouse Report. Lighthouse also investigated neural networks, and he told the British, he said, no, this is no good. Quit the funding of it. But the sad part is that by doing this attack on neural networks, Minsky and Papert also killed their own funding. And so all neural network funding, all rule-based system learning just went, I don't know, it just turned to ashes. So this was the Minsky-Papert objection, and this is the one everybody repeats when they talk about the downfall of neural networks. But then in 1975, Paul Werbos was the first to come out with a way to overcome the Minsky-Papert objection. And he said, let's add these things called hidden layers. Later, this was popularized by David Rumelhart and Jeffrey Hinton in the so-called PDP books, which everybody read. And in fact, there's some people, I just read an article that Jeffrey Hinton is, after being credited with inventing backpropagation, says, no, I didn't invent backpropagation, which he didn't. And it was Paul Werbos in 1975. But it took a while to discover what he did. But here's the idea. Let's add these hidden layers now, and we're going to make this thing nonlinear. And we're going to make it nonlinear so that we're not restricted to have these classifications that are simply lines. So we're going to have hidden layers, and we're going to have output and the input layer with these hidden layers in between. And the key was that Werbos came up with a way of training this neural network that preserved this localization and training. Specifically, two neurons, the interconnect between two neurons was only determined by the neuron on one end and the neuron on the other end. And so it was all a localization in training. And this is dominated as the training algorithm, which is today still used in deep learning, as we'll talk about. So I gave you a copy of my book, Neural Smithing, which you see in the background here. But this is, I think, maybe the easiest way to think about training neural networks, because you get really screwed up in the notation because you have all these subscripts. You have the subscript of which layer you're in and which weight you're in, and all of these different things. This, which was due to Russ Reed, brilliant young man, is simply arrange your neurons, and you can always do this. So, and label your neurons, 1 in this case through 16, and always have a lower neuron number connecting to a larger neuron number. Now, there are recurrent neural networks where you have feedback, so the 11 might come to the 6, but this is the case for so-called feed-forward or memoryless layered perceptrons. And you also have the bias node here, and the bias node is labeled to 0, and this bias node connects to every neuron in the neural network. But again, the idea is that a higher level neuron does not provide an input to a lower level neuron. And so if you do this, you only have to keep track of one subscript, and that is the subscript of the neuron. So the math, I think, is easier. So here's what happens. There is something which is called Aerobatic Propagation, and the basic idea behind error propagation, behind neural network Aerobatic Propagation, is there is a forward pass. In other words, you put an input and you get a so-called output. And then the output is compared to the input. And you look at the difference between that, and that is the error. So you can compute the error associated with this particular input. Then there is a second term, and this is where the idea of aerobatic propagation has. You have the error, and you go backward through the neural network, and you go backward through the neural network and paint all of the neurons. Going forward, each of the neurons is given a number. Going backwards, each of the neurons is given another number. So each neuron is given two numbers by this back propagation. And then if you want to do something like, let's see, I want to change my color here. Okay, I don't know how to change my color. Okay, anyway, if you want to change just the weight of this neuron and the weight connecting this neuron and this neuron, which turns out to be this weight, right? The beauty of aerobatic propagation is you only have to know a single number here, and you only have to know a single number here, just like in the non-layered perceptron or non-layered neural network. And you can update this interconnected weight just by knowing what is happening at these two neurons. And that is beautiful. If you don't use aerobatic propagation, you got to know what's happening all over the neural network. And therefore you have to characterize it by these enormous matrices and, you know, higher dimensional representations. And that just gets really, really rough. So here's what happens. And this is done through partial differential equations. There is the feed forward. Whoops, where'd we go here? This is the feed forward representation. Oh, I did find the place where I can change it. Okay. So this is the feed forward where we're going from the input to the output. Okay. So we have all of these Ys. Now, what are these Ys? These Ys are all of the states which are feeding the neural network. So each neuron has a state, and we'll call that Y sub I. This is the number which is painted with the forward progress of the training. So each neuron is allowed a value of Y sub I. And neurons or inputs can provide states which feed other neurons. This is the idea, of course, of the so-called McCulloch-Pitts algorithm. And so it has a activation, A sub I is the activation, but we don't like that because these can get really big. So we run it through a squashing function here. Here's a squashing function. And that makes it into a smaller, more manageable number. And then this number is broadcast to other neurons to which this is connected, right? And so we can do this very easily from neuron to neuron. We know the mathematics of the forward. The beautiful aspect of this is the aerobatic propagation. And my screen froze again because it doesn't like me. Maybe it just doesn't like purple. I think it doesn't like purple. And then the beauty of the aerobatic propagation, which was denoted by, well, what the heck's going on? Oh, okay. These nuances are killing me. What happened is I put it on the presentation mode, and it just screwed everything up. Okay. Now I got my mojo back. except now it's not letting me do anything. I don't want to draw. I want to go backwards. Okay, I don't care. Yes, I do. Thank you. Thanks everybody for your patience here. Okay, we're back here again. Okay, so the aerobatic propagation, this was the big discovery of Wurbos, later popularized by people such as Rumelhart. Oh man, I hate to do this. It's the computing of these dells. These are error derivative terms. Remember I said that these sigmoids were very nice because they differentiated very nice? Well, a lot of that is due because of these delta functions. We said going forward, you compute all of the values of y. Going backwards, you compute all of these error functions, which are derivatives, which are error derivatives, but we call them dells. And we can do this for we can do this for the output. And this was known by Woodrow. Remember we said that if we take what you want minus what you get, that we can actually use that as the update for the output layers. We go backwards. Well, what Wurbos did is he found out that we could propagate these delta i's, these energy terms, by a process kind of like the feed-forward McCulloch-Pitts algorithm. We simply needed to look at all of the elements that fed a neuron. Now we're coming backwards now. So these are all of the neurons which this neuron fed. And we're coming back, we sum them, we run them through a different nonlinearity, which turns out to be the derivative of the nonlinearity that we used previously. So if we use the sigmoid, this would be the derivative of the sigmoid. If we use the hyperbolic tangent, it would be the derivative of the hyperbolic tangent. And this then is broadcast to all of the elements that fed this neuron. And now we have it all. We have the Y's and we have the deltas. And that's the beauty of aerobatic propagation, because it turns out just the deltas and the Y's are needed for the corresponding updates. And let's see, the screen is frozen again. Okay. And for every case, our step downhill, remember our step downhill is equal to delta I times y sub j. So in the feed forward part, we compute these y sub j's. On the aerobatic propagation, we compute these delta j's. And then our weights can be totally updated. Our weights can be totally updated just by knowing what happens on either end of the interconnect. It's a beautiful mathematical result. Now, there's some problems associated with it, one of which is, well, overshoot, if you will. And steepest descent, this is steepest descent that we have here. Okay, it doesn't like, maybe it'll like red. Let's see if it likes red any better. This is steepest descent, where we have the updates, the weights being updated by the step size. Don't forget that we do have the step size times whatever the change in weight is computed to be, which is a function of those dells and y's. And there's something which is added also, which is a momentum term. And I'll show you the importance of the momentum term. The new step is affected by the previous step. The way that the neural network is set up right now is that you could have, first of all, an adjustment of the weights that took you this way, then the new adjustment of the weights took you way over here, and then a new adjustment took you here, and you got a zigzag thing happening. And there's different ways to overcome it, but one of them is to add this momentum term. The momentum term says that your new step must have a part of it that is equal. Your new step must have a part of it that's equal to your old step. So your new step is equal to your update plus a little bit of your old step. And the trade-off between those is determined by this value of alpha. Okay. Let me show you some of the, what I'm going to do, I'm going to try to share my screen, see if that's any better. Okay. And I'll show you what happens. This, by the way, this is what the idea is if you choose your step sizes too big, too small, and just right. It's like a Goldilocks sort of effect, right? You can get underdamped, overdamped, and you can get critically damped. Now, there's another way to get around this besides momentum is to use batch training. The way that we presented, we put an input and then we updated all the weights. We gave another input and we updated all the weights. Batch training, you accumulate an error from a subset of the training data. So if you have like 20,000 training data, maybe you choose 1,000 of them and you run it through, but you don't update the weights. You just accumulate the error on the output. And once the error on the output is accumulated from 1,000 different iterations, then you do the aerobatic propagation. Okay. What I was talking about and what we kind of implied here is that we had online sort of training. That is, every new input gave you an update. So that's a rough way to do it, but sometimes it's necessitated. Here's an example for online training where you have a list of data and you're training the neural network with it. And in this case, you can see it's very jagged. And what this does is it goes through the list of data, then it goes through the list of data again, then it goes through the list of data again. And because the same data is used in the same order over and over and over and over again, we have this cyclic thing, right? We get to the end, we go back to the beginning. Well, it kind of does what it did before as we step through the data. And so to get away from this to this randomization, if you are using online training, that is training one data point at a time, you should probably do something like shuffle your data every time. That is, you know how to shuffle data, by the way?
Just present it in a random order.
Yeah, you take the data, generate a random number, and then generate or sort the random number generator from smallest to highest with the tag-alongs coming along with you. But anyway, this is what you get if you do that. And another way you can do it is just to simply choose at random a input instead of shuffling every time. Just choose a random input. Choose this one, this one. Yeah, sometimes you might choose the same input 2 or 3 times, but you know, on the average, statistically, every input's going to be used as much as every other input. So that's what you get here with this online training data at a time. You get something more like this, which is okay. I'm reading. I think this is the batch training. Yeah, this is the batch mode back propagation, where you use in this case, all of the data was used, the error accumulated, and then the back propagation occurred. Then all of the data was presented again. The error was computed and aerobatic propagation was applied. So it isn't applied every time. The error accumulates before it is used for the aerobatic propagation. So these are the 3 different examples we get here. This is the top one is just doing everything in a list over and over and over again. And since we don't shuffle that list every time, we get this kind of a periodic ratcheting here. This one, we do shuffle it, but even though we shuffle it, data can be contradictory sometimes. And whereas over here, we use the batch training, and the batch training converges much more smoothly, as you can see. You got to be careful here, though, because each one of these corresponds to a single pass through the neuron or through the neural network, whereas here, one of these passes might correspond to 20 or 30 passes through the neural network, right? So you can't compare the dots one at a time. Okay, let's see. We got about 15 more minutes left. So let's talk about learning versus memorization. We talked about that a little bit in the introduction to classifiers, but we do not want to have, I'm going to go dangerous here and I'm going to go full screen. We do not want to memorize what's going on. Whoops. And what do I mean by that? Let's look at all of the yellow dots and the yellow squares. Forget about the green data. Forget about the green right now. But you see that big pink blob that's there? That represents exactly all of the little circles. Do you see that? So why is that right? And instead of the dashed green line? Why is the dashed green line better than the big blob? And what do we do to ensure that we don't get big green, big pink blob, to make sure that we don't get this great pink blob that looks like a bug that somebody stepped on, and instead get the dashed line, the green line, that is a more reasonable value? There's something kind of similar too. And here's something similar. We have a bunch of dots just on a plot. And here, these are yellow dots. And we could fit that pink line to it, right? That pink line passes through all of the points. And certainly that pink line would give us 0 error. But it doesn't look like it's really learning. It looks like it's memorizing. It makes more sense to have that green line. In other words, something which is smooth. How do we assure that? We assure that with something called, let me go through this list first of all. Learning versus memorization. We want to recognize data outside of the training set. In other words, if we do sumo wrestlers and basketball players, if we get a sumo wrestler we haven't seen yet, we hope that it's classified as a sumo wrestler. So it has to be able to recognize things it hasn't seen before. That's the test of learning versus memorization. How can we assure learning? One is by cross-validation. The other one is by choosing neural network structure. And we're going to talk about cross-validation here next. Here is the idea. When you have test data, you separate your test data into training error, into training data and test data. And by the way, this is, I don't know, things change. This is sometimes called validation data. So they're different terminology. But we're going to talk about dividing your data into training data and test data, recognizing that this test data is sometimes referred to as validation data. Now, the training data is going to be used to train the neural network. The test data is not used to train the neural network. And what we're going to do is we're going to train the neural network, and we're training the neural network, and this error, and by the way, I didn't label my axes, which is a no-no. This is the error associated with the number of weights, with the weights that we're talking about. And we can train and train and train and train. But every time we train and we do an aerobatic propagation and update the weights, we submit the test data to that. Now, don't forget, the test data is not used to train the neural network, right? The test data is not used to train the neural network. Now, what happens is that if your neural network is too big and has too many degrees of freedom for the data that's being used, it turns out this will go down and down and down. And eventually, when it gets down here, it'll be doing memorization. What we want in learning is for the neural network to understand data that it has not seen before. And that's where the test data comes in. The test data is also used as we train the neural network, and it gets to a point where you get a minimum here. And then as you memorize, it does work. The neural network does worse and worse on data which it hasn't seen before. Does that make sense? So therefore, we would like to choose this point, whatever weights are given at this point where the test data is at minimum, those are the weights that we should use for our neural network. Unfortunately, this procedure is not used all the time in deep learning, but it's something which it should be. But this is the way that we make sure that we are learning and not memorizing. You've heard of deep neural networks making problems when a single pixel on the input is changed. If you're recognizing cats and dogs, a cat, which is recognized, will change to a dog if you just change a few pixels. That's because there really hasn't been this cross-validation which has been applied. Okay, so here is the other thing. How do we do the testing? Here is the visualization of the testing. Remember this over wiggly curve here that we had? And we want to make sure that we get the green curve and not the pink curve. How do we do it? We choose a bunch of things which are outside of the training data. All the yellow dots are training data. We're going to choose test data, which are the red dots. And as we train, the error associated with the red dots, which are not being used to train, need to be small. You'll notice that the error associated with the red dots and the pink curve is going to be very large, isn't it? So even though the neural network with the squiggly pink line has memorized, it fits all the curves very well, it hasn't learned. Why hasn't it learned? Because it's not doing well on the test data that corresponds to the red dots that were not used to train the neural network. So in wiggling around, we want to keep track of both of these, both the training set, training data, and the test data error, in order to make sure that we are learning as opposed to memorizing. Next thing I would like to talk about is the so-called curse of dimensionality. This is a problem which was an Achilles heel to neural networks until some more clever techniques came down the road, such as the convolutional neural network. Let's take, for example, the following question. How many points do we need? We have yellow points and black points. And what we want to do is we want to train a neural network to recognize points within the circle as opposed to points external to the circle. Now, forget the circles there. Try to get rid of it in your mind and kind of squint and ask yourself, how many points would we have to get in order to, if we squinted, to recognize that the yellow circles corresponded to a circle? And there's no clear answer, but I'm going to say 100 points. We kind of have enough points here to see that the yellow circles, the teeny yellow circles are forming this large circle, and the green dots are external to that. But you notice it takes what? 100 different values, right? Or 100 pieces of training data in order to assess that. So this is in 2 dimensions. So if we have in 2 dimensions, it takes us, if you will, 10 squared points. Let's go to 3 dimensions. We're going to generalize our problem to recognize that all of the dots are within a sphere as opposed to external to the sphere. How many points are we going to need here? This is the amount of training data that we're going to need in order to train with the points, or differentiate between the points in the sphere and external to the sphere. I know this doesn't look like a sphere, but use your imagination here. Well, it's kind of like we have 10 different layers here. And if we take 10 layers and apply 100 training data points, which is what we did in the 2-dimensional example, well, that turns out that we're going to need about 1,000 points. So if we have 3 inputs to the neural network, I1, I2, I3, corresponding to, you can see it's labeled here. It's labeled I2, I1, and I3. In order to differentiate between the between the points internal to the sphere and those external to the sphere, we're going to need about 1,000 points. Whereas here, we only have this input and this input, and we need about 100 points in order to do it. So we can see what's happening here. We have a progression. We have 2 points in a progression that can easily be shown as going to 10 to the n points, 10 to the n. So therefore, if this is the curse of dimensionality that we saw with pancakes. Remember, we added ingredients and how much more difficult the testing of the pancakes would be. This is a different manifestation of that same curse. So if we're going to have 1,000 inputs into the neural network, we're going to need 10 to the 1,000th training data points. Now, what I'm presenting to you here is just a geometric rule of thumb. Often you can get away with a lot fewer than that. But the purpose of this is to present the concept of the curse of dimensionality, and the reason that we need to be very judicious in the choosing of our number of inputs. Again, convolutional neural networks wonderfully get around this problem. But prior to things like the convolutional neural network, if you wanted to train the difference between sumo wrestlers and basketball players, you could not put in pictures of sumo wrestlers and basketball players. You couldn't do it. There would just be too many pixels, too many inputs for that regular vanilla neural network to process. It would be 10 raised to, well, probably even bigger, but 10 raised to ever how many pixels you had. You had to have an enormous number of inputs. Rather, what you did is you looked for something called features. What characterizes a sumo wrestler and a basketball player? We've already done that. We want to boil away, using our expertise, all of the details of sumo wrestlers and basketball players and say, well, you know, the weight and the height, those are things we can do. So instead of doing the pictures, we just do the weight and the height, and that's enough to train the neural network because the number of inputs now is down to 2. That's something that we can imagine. Okay. Yeah, so this is a deep convolutional neural network, and we will go into those later. Here is principal components. Let me check my time here. Okay, we have enough for this. Principal components is a statistical method which is used a lot for the following case. Suppose that you have a 3-dimensional surface here, okay, or 3-dimensional data. Let me go up here and change my color. Oh, it did come out. Okay, I don't know what's happening. Okay, so you have 3-dimensional data, but it turns out all your data lie in a plane. And if you looked at this plane, most of the data would lie on this plane. It isn't necessarily parallel to anything, but all the data would lie on this plane, except there would be a few points that, you know, they'd be a little off the plane, but not a lot. So for all intents and purposes, all of the points lie on the plane. So all of a sudden, if you're clever, you can reduce the number of dimensions from 3 to 2. If you figure out some way to get that 3-dimensional data down into 2 dimensions. And this is referred to as principal components. Here's on the left is an example in 2 dimensions where most of the data lies along this, looks like a 45-degree line. And there's some variation along this line, but maybe we don't need that information for the classification. Maybe just this along this one line is sufficient enough. And so the question is how do we choose this lower dimension? And that is what is used in principal components. So principal components, here we go again. Whoa, I didn't even mark on that yet. And here we have it. Okay, principal components looks at data, and here's your data, and here, okay. Anyway, you place your data in a matrix, and you can generate the principal components if you have your data in this matrix. This is a correlation matrix, and you can compute the so-called eigenvalues of the data. And what you want to do is you want to choose the big eigenvalues, because the big eigenvalues correspond to lots of data is in that dimension. And therefore you can do it that way. I'm not going to go through this too much. But I will say, look at that. That notation is just carrying on. Wow, we have memory here. I did want to touch on this really interesting example called autoencoders. If you watched Justin Bowie's PhD presentation the other day, you saw that we could indeed do autoencoders, and he did use autoencoders. But this is a very curious way of doing things, because for an autoencoder, the input is equal to the output. The input is equal to the output. Why would you ever want to train a neural network? Why would you ever want to train a neural network where the input was equal to the output? That's the question before us. Typically what happens in the autoencoder, and this is done in all sorts of different flavors, deep convolutional neural network autoencoders, for example. What you do is you chose your hidden layers so that you come down here to something called a latent space. Now, this latent space is in the neural network, the waist of the neural network. This is where the neural network gets the skinniest. This part here is referred to as the encoder. And from the latent layer output is referred to as the decoder. So the question is, what is the importance of this? The importance of this is right here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 outputs, or I'm sorry, 10 inputs. And we want to train those 10 inputs to generate the same outputs, right? But notice what we've done by making this into 1, 2, 3, 4. We have reduced a 10-dimensional representation to a 4-dimensional representation. Because all of the we only need the values of this information. We only need the value of this information to generate the output. And so that's the beauty of the autoencoder. Is one of the things, we talked about the dimension of the input. If you can subject your training data to an autoencoder, you can train the neural network on this as the input instead of this as the input, because in terms of information, we know that this latent layer, the smallest layer, contains the same information as this other layer. Isn't that fascinating? And what this does is, the way that I visualize it is that in this higher dimensional space, if this is input 1, input 2, that red on black looks kind of cool, doesn't it? That there is this kind of manifold. Now I'm only doing it in 3 dimensions. There is this manifold, and all of the data kind of lives very close to this manifold. And what you're doing is you're learning this manifold as a compressed version of the entire data. Now, for principal components, it turns out that this manifold is it can only be a plane. But it turns out if for an autoencoder, because of these nonlinearities, it's no longer restricted to a plane. In fact, there was this great Finnish Erkki Oja, I think it's OJA, that did a lot of work in showing that the autoencoder with no nonlinearities basically gave the principal component result. In other words, it gave the data which lied on the plane. But the autoencoder more generally with the nonlinearities gives us these nonlinear manifolds on which data live. But the important thing is that the 4 numbers here contain the same information as the 10 numbers here. And why is that? Because we can take these 4 numbers and through the decoder, we can compute the output. We can compute the output, which is the input. there's a lot more interesting applications of the autoencoder, and we'll talk about that next time. Any questions at all?
I have one. So if you're going to make an autoencoder to try to parse out the principal components of a data set, will there be data sets that you can't do that? Like if there's too much information in the inputs and you can't narrow it down to just a few neurons in the latent space, will it just fail?
Yeah, well, here's what's interesting. Suppose that your data lies on this kind of, I had it in a previous slide, didn't go through it very much, but lies like on a parabolic surface. Principal components won't get you that parabolic surface. It can only work if there is a linear, a plane. It only works on a plane. Whereas the autoencoder can give you this, this twisted sort of thing. And if you want to use principal components, do it. You know, it's very easy. There's canned programs that allow you to do it. It's just some very easy math manipulations, matrix manipulations, just perfect for MATLAB. And you'll notice in all of these neural networks, we have left a number of questions unanswered. If you have a specific data set, how many hidden layers do you use? How many neurons do you put in each hidden layer? What do you choose as the step size? What do you choose as the momentum, right? And these are all questions that have to be answered. And any training algorithm requires this, and any neural network algorithm requires this. So you have to, that's the reason my book, which I gave you a copy of, by the way, in the sheets, you're welcome, goes through and talks about neural smithing, how you literally figure out what to do and how to craft your neural network. Any other questions or thoughts?
I have kind of a quick question related to this sort of analog of the principal components and autoencoders. So in like a single layer neural network, you can basically, at least from my understanding, perform like kernel PCA on sigmoidal kernels, and that actually gives you the essentially output equivalent to a single layer autoencoder. I'm curious, like, has that result been generalized to like deeper autoencoders, or is there some kind of approximation result that's...
You know, there's an interesting theorem which was popularized by Robert Hick Nielsen due to a theorem by Kolmogorov. And this result is that any problem you look at in the world can be solved by a neural network with a single hidden layer. I'm not talking about autoencoders, but I'm talking about general neural networks by a single hidden layer. And that's pretty astonishing results. However, like many such general results, it really doesn't address the question of the architecture and what goes on in the architecture. It turns out that you might need, and I'm making a point by exaggeration here, for your problem, you might need 1,000 neurons in your hidden layer, according to Kolmogorov. Whereas if you're smart and you craft your neural network properly, you can use 2 hidden layers, maybe with 3 neurons and 2 neurons. So yeah, as far as the generalization goes, I don't remember the details of Urquiolla's work, but I do know that he showed an equivalence between the autoencoder and principal components. Any other questions? Okay. Be of good cheer. Bye-bye.